Here we have Alice and Bob. Alice and Bob have a shared secret represented by this key, so Alice can encrypt a message and send that message over to Bob. How does Bob know that that message is from Alice and as Alice intended? After all, Mallory could encrypt a different message and send it to Bob. At least with the ciphers that we looked at so far, any stream of bytes will decrypt as something. So Mallory may have mangled the message that Alice sent or may have constructed a different message. So how can Bob be sure that he gets a message from Alice as Alice intended? One possibility is to add something at the end of the message that Bob will recognize because it's another shared secret, a different key, and the only way to get that key there is to have known what it was. If you're using a block cipher with a mode of operation, then this can work because any change earlier in the message will also affect the part of the message that's supposed to have the key. And so if Bob sees the key at the end, then with very high likelihood, all of the message before it was also as Alice intended. But that's no good with a stream cipher, because in a stream cipher, Mallory could change the middle part of the message and leave the key intact. So we're looking for a more general mechanism and one that specifically addresses the problem of integrity. So the solution we'll look at today is called a cryptographic hash, represented by this function h. H is going to take our message and is going to take this extra shared secret, and it will give us back a small summary of that message in the form of a hash code. And when we use a hash code for this purpose, then it's called a message authentication code, or MAC. Not to be confused with linked level addresses, but in cryptography, MAC means a hash used to ensure integrity of the message. So Alice will include this MAC at the end of her message, similar to including the shared green key. But now, even if we're using a stream cipher, then that purple block summarizes everything that came before it. So we don't have to rely on a mode of operation or something like that. Instead, we have a direct solution because Bob can hash the message along with his private key to make sure that combination matches the purple block that was sent. Why do we mix the key in to the hash function instead of just summarizing the message? Because it's only the message summary that we cared about. By including this extra shared secret, Bob makes sure that Mallory hasn't just constructed entirely different bytes and put a MAC at the end of it. So it gives some extra assurance that not only is it as Alice intended, but started from Alice, which moves us a little bit in the direction of authentication instead of integrity, but these things all fit together, and that's why we want to include the key in the MAC now.